Today's lesson is going to be about reviewing things called linear functions. And you spent a lot of time in Algebra 1 talking about linear functions, so it's worth taking a few minutes here just to review some of the concepts that surrounded this idea of linear functions. And basically, I'm going to be taking almost like 2 or 3 units worth of Algebra 1 and cramming it into this little lesson review video, okay? So the first thing that we need to understand is, well, when we say linear functions, what is exactly what we're talking about? So what is linear? Like, what makes something linear or makes something a linear function? Well, we need to remember that on inspection, if we're looking at a function or we're looking at an equation, what we'll notice is that there is no exponent in the equation higher than 1. All right, no exponent higher than 1. That makes something linear. Once we start raising the exponents on variables, then we start calling them things like quadratics or cubics or things like that, right? And then if we were to graph a linear function, what we would notice is that the graph would be of a straight line or part of a straight line. So a straight line or part of a straight line. Now this is what it looks like on inspection, right? So just by looking at an equation or a graph, we can tell that it's linear. But what exactly makes something linear is that the two variables have a constant rate of change. Have a constant rate of change. Right? So the difference between one variable to the next is never going to change. It will always be the same. Now, we use this word rate of change a lot in math, but you also know this as the slope. The slope of the line, in this case, is constant with a linear function. We've written linear functions in different forms, right? So, for example, you wrote 3 different forms for linear functions, 3 different forms. The most popular one that you see quite often is something called slope-intercept form. Slope-intercept form is the famous y equals mx plus b. Y equals mx plus b, where m is the slope and b is the y-intercept. The y-intercept, of course, is where the line crosses that y-axis, or it's the y value when x is equal to 0. Another form that you may have written it in is something called point-slope form. Point-slope form looks something like this. Y minus y sub 1 is equal to m times the quantity x minus x sub 1. Okay? Where the point, a point on the line, has the coordinates x sub 1 comma y sub 1. And of course, there's that slope again in point-slope form. The last form is something called a standard form. Standard form is a little more unusual. It looks kind of like this. ax plus by equals c. So there's no slope obvious in this equation. No slope obvious in this equation, but you can find the slope in there. And we'll talk about how to do that in just a little bit. But something I want you to notice about this is that both variables x and y are on one side of the equation. Both have some kind of coefficient, a and b. The one thing we need to remember is that with our leading coefficient a can't be a fraction or a decimal. And if that's the case, then you're going to need to change this so that it doesn't have a leading coefficient that's a fraction. That's sort of simple to do. You just multiply every term. Multiply each term by a common denominator. And doing that will allow you to just eliminate all the fractions, or do something that we call clearing all the fractions. So these are the three forms that we can write linear functions in. Now I want to take a few minutes and just review the idea of slope or rate of change, right? We can use those interchangeably, the slope or the rate of change. Of course, we use the letter m, and we can define the slope in a few different ways depending on what sort of model we're looking at in our linear function. But in general, right? So the definition can look like a couple different things. In general, we can write it like this: delta y over delta x, where delta represents the change in, right? The change in y over the change in the x's. And I'm using y and x because most likely we're going to be using those as our two variables, but they really could be any two variables that we're looking at showing the relationship of. So slope can be the change in y and the change of x. That's the general form. If we're looking at a graph, right? If we're looking at a graph, the way we interpret this is the slope is the rise of the line over the run of the line, right? The rise over the run. If we're looking at like 2 points, maybe we want 2 points on the line, maybe we want to interpret our slope as, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. This would be, again, the change in the y's over the change in the x's, but now in a more algebraically set fashion. Things to keep in mind when it comes to slope. So not all lines are going to have a slope, which is easy to find, but I do need you to remember that horizontal lines, so remember that's perfectly horizontal, they have a slope of 0. There's no rise to that line, so it would be 0 over some number, and 0 over anything is 0. But on the other side, vertical lines going up and down, they have no run. They don't run anywhere horizontally. So the slope would be something over 0, and we hopefully understand at this point that we can't have 0 as the denominator of a fraction. That's not even a real number. So what we say is the slope is something called undefined. Undefined slope, vertical lines. Okay? So how do we find slope? Let's look at a few examples of how we actually might find slope with these definitions. So let's say, let's look at a table of values. Let's say we have x, y, here's our table of values, and let me just take a second and fill in a few values here. Okay, so here's my table of values, and if I ask you, all right, find the slope of the line which contains these points. Well, first of all, it's a little presumptuous of us to say that this is a line. Just by looking at these points, I don't know if we would be able to say, hey, this is a line, unless we actually did a little investigatory work. So remember that the slope of a line has to be constant. The rate of change has to be constant. So this delta y over delta x has to be constant. And if it's not constant, then we're not talking about a line. So we have to find delta y and delta x first. So what I'm going to do is I'm just going to find the difference, the change in the y's every time. So from 2 to -1, we go down 3. From -1 to -4, we go down 3. From -4 to 7, we go down 3. Okay. And now let's find, so this is delta y. These are the delta y's. Let's look for our delta x's. 1 to 3, we go up 2. 3 to 5, we go up 2. 5 to 7, we go up 2. So the rate of change each time, right, let's remember this, the rate of change here would be -3 over 2. The rate of change in this one would be -3 over 2. The rate of change on this one would be -3 over 2. So because the rate of change is constant all the time, we can say, yeah, okay, this is a linear function, and the slope of the line would be negative 3 over 2. It's really important to just double check this rate of change, okay? Because sometimes you're not giving consecutive numbers or consecutive points on the line in your table of values. And it appears on the surface sometimes that the rate of change is not constant, but if you look a little bit closer and you actually find the ratio of delta y to delta x in every single set, you may find that it actually is constant. So let's say this is our line now, okay? So this table represents points on our line. We found the slope of negative 3/2. Well, what's the equation of this line? Like, what's the equation? I'm going to change this to black here. What's the equation of the line which contains those points? Equation. How do we find it? Well, remember, we can write our equation in slope-intercept form, point-slope form, or standard form. Doesn't matter. Slope-intercept form is great if we know the slope and the y-intercept. Point-slope form is great if we know the slope and the coordinates of one point on the line. Standard form, generally speaking, is derived from one of the other two forms. So if we're given a table of values, which one of these forms actually makes sense to write first? How about point-slope form? Since we already know the slope is negative 3/2, and we can choose any one of those 4 points to be the point in our point-slope form, let's go ahead and write the equation of the line. So we have y minus, I'll tell you what, let's use 1, 2. All right, so we're going to use 1, 2 as the point. Remember, this is x sub 1, this is y sub 1. So the equation of this line would be y minus y sub 1, which is 2, equals the slope, which is negative 3/2, times the quantity x minus x sub 1, which is 1. This would be the equation in point-slope form. Now, from point-slope form, we can change it into any of the other forms, right? We can convert this into slope-intercept form. So let's just acknowledge that this is point-slope form. But what if we wanted to know what the y-intercept was? Point-slope form doesn't tell us. So how do we go from point-slope form to slope-intercept form? Well, it's just a little manipulation here, just like a literal equation. Essentially, what we want to do is just isolate our y, right? So I'll tell you what, first we'll do a little distribution. So negative 3/2 times x is negative 3/2 x, and negative 3/2 times negative 1 is positive 3/2. And then we just need to isolate that y. So what I'm going to do is I'm going to go ahead and add 2 to both sides. And I get y equals negative 3/2 x plus 2 plus 3/2 is 7/2. So now that we have it in slope-intercept form, we can identify the y-intercept, right? The y-intercept here would be at the coordinates 0, 7/2, because that, b, is our y-intercept. Now, the last form is standard form. So how do we get to standard form? What if I wanted to write this in standard form? Well, remember, standard form has both my x and my y variables on the same side. So what I'm going to do is I'm going to take the x term and I'm going to move it to the other side. So I'm going to undo it by adding 3/2 x to both sides, plus 3/2 x, plus 3/2 x, and I end up with 3/2 x plus y equals 7/2. Remember before, you can see it, I kind of have it in green up here, or excuse me, in blue. Remember before I said that the coefficient of the x term can't be a fraction or a decimal. So if it is, we need to multiply each term by a common denominator. Well, in this case, the coefficient of the x term is a fraction, and I need to clear that. So what I'm going to do is I'm going to multiply every term in the equation by a common denominator. Both fractions in this case have a denominator of 2. So the common denominator is going to be 2. I'm just going to go ahead and multiply every single term in there by 2. So 2 times 3/2 is going to be 3. we get 3x plus, and then 2 times y is 2y equals 2 times 7/2 is 7. What ends up happening then is we clear all the fractions, and all of our coefficients are now integers. So these are the three forms. Okay, these are the three forms of linear functions and how to write them. Of course, we can, if we want to go back and talk about slope for just one more minute, I know we said that if you're looking at a graph of a line and you're asked to find the slope, you need to find the rise over the run. So let's just consider this point here. Any 2 points on the line, right? You start the leftmost point, that's your rise, and then you go from there to the right, and that's your run. Pay close attention to the signs here, right? Going up is positive, going right is positive. If you're going down, that's negative. If you're going left, that's negative. So it's important that we acknowledge what those actual signs are. The one last thing we need to talk about are parallel and perpendicular lines. Let's just remember that parallel lines will never cross. And if they never cross, it means that the rise and run of one line would be the same as the rise and run of the other line in order to stay the same distance apart. So parallel lines have the same slope. They have the same slope. Perpendicular lines, on the other hand, perpendicular lines will cross, right? Their slopes are going to be opposites and reciprocals. Opposites and reciprocal slopes. And what does that mean? Okay. Well, for example, let's say I have a line and I know that its slope is 2/3, right? So if I have a line and I know its slope is 2/3, what would be the slope of a line that's parallel to that line? Parallel lines have the same slope. So parallel lines will all have the same slope of 2/3. But what if I have a line that's perpendicular to the original line? What would its slope be? Well, again, they're opposites and reciprocals. Opposites, I mean opposite signs. Opposite signs, that would make it negative, and the reciprocal would make it 3/2. So the reciprocal opposite slope or perpendicular of the perpendicular line would be negative 3/2. Another way that we can think about it is that if we have the slope of an original line and we multiply that by the slope of the perpendicular line, we will always get -1. So the product of the slope of a line and any perpendicular will be always -1. One last problem. One last problem. Let's say I have a line that has the equation Rx plus Py equals S. And I know that R, P, and S are constants, meaning they're just numbers. Okay, they're just numbers that aren't going to change. And X and Y are my variables. So these are going to stay as the variables. Right? What is the slope? What is the slope of this line? Now I know we don't have any numbers here, but that doesn't mean we can't find a representation of this slope. Well, how do we find the slope here? We have a couple different ways that we can go about doing this, but it all goes back to one of our original forms of the three lines, slope-intercept form. Remember, that's y equals mx plus b. If we can rewrite this equation so that it's in slope-intercept form, then all we would need to do is be able to identify, well, what's in that spot in the equation where m generally is, right? So I'll tell you what, let's rearrange this so that it's in slope-intercept form. I'm going to move this whole this whole term, negative rx to the other side, and that's going to leave me with py equals. Now remember, in slope-intercept form, the x term usually comes first. I mean, it doesn't really matter as long as you identify it and you know which term is which, but I like to put it first. And then we're going to go ahead and divide every term by p, divide everything by p, and we get y equals negative r over p x plus s over p. Now it's in slope-intercept form. Well, where in this equation is the slope, right? The slope is where m usually is. And if we look where m usually is, we see the fraction. The slope here is negative r over p. Negative r over p. Which is interesting because the original problem, the original one, was almost in standard form, isn't it? Standard form. And look at what the slope ended up being. It ended up being the negative of the coefficient of x over the coefficient of y. That might become useful because if we have something in standard form like ax plus by equals c, we might be able to just shortcut that and say, well, what's the slope of the line with this equation? Well, we can do what we just learned, right? The slope is going to be the negative of the coefficient of x over the coefficient of y. So the slope could be shortcutted to just say, oh, the slope is negative a over b. Could you think of what we might be able to shortcut the y-intercept to be? I'll give you a hint. Look back here. Right? The y-intercept was the constant over the coefficient of y. So what would it be if it were in this form? It'd be c over b. Now, I know this was a long little review of linear functions, and there's some more stuff that we actually are going to be looking at with linear functions. But hopefully you jotted some things down just to refresh your memory. Maybe there was something new in here that you didn't know before, or that you weren't taught, that suddenly you made a connection. That's my hope. That's my hope.